I'm going to talk to you about LLDB in FreeBSD, but in order to get there, I'm going to talk a little bit about the history so that you'll understand how we got to where we are and how that relates to where we hope to go in the future. So first of all, why do we need a new debugger? As you know, a characteristic of BSDs is the concept of a base system, a cohesive set of operating system components that are developed and released and debugged and built together and released as an integrated whole. And so one of the components of the base system is the tool chain, which includes the compiler and the linker and all those things, and of course a debugger. And FreeBSD has a long history with GDB in the base system, the GNU debugger. So the history actually goes a little bit further off to the left of this chart. I mined the contrib/GDB directory to find out exactly when GDB releases came in over time. And the very first FreeBSD release actually predates the way that the source tree is used now. So I booted up a FreeBSD 1.0 ISO image in a VM to see. And FreeBSD 1.0 in 1993 had GDB 3.5 in it, and then in 96 we imported the source for 4.16 into FreeBSD. So the light blue bar on the top represents upstream releases, just selected ones, and then the maybe that's fuchsia or light purple bar down below represents the time at which we imported that release into FreeBSD. So over time, GDB releases would come out, new minor releases would come out, and they'd get imported. So we skipped a little while, and then 4.18 came out, we imported it. A new major version came out, 5.0, and we imported it. And each time this would happen, we'd have a bit of work to do to adapt the new release to run properly on FreeBSD. So the sorts of things that had to be done are support for FreeBSD's threading model, support for kernel debugging. All of that didn't exist in the upstream GDB project. And then as time went on, additional GDB releases came out, and we imported them. Basically, once every year, once every other year, sort of thing, a GDB release would get imported into FreeBSD. And over this time, this patch set for supporting GDB on FreeBSD kept growing and growing, and was a larger amount of work on each new import. And all of this history predates my direct involvement with debuggers on FreeBSD. So I don't have a direct reference, but I talked to the people who were doing the work at the time and asked for a little bit of the history. And basically, the developers who were working on GDB and on FreeBSD at the time tried to work with upstream GDB to get the patches pushed upstream, because of course it's a lot less effort if the changes for your own OS are integrated directly in the upstream project. If you have to, every time a new upstream comes out, do a whole bunch of work to bring it into your use case, then it just becomes a larger and larger and larger maintenance overhead. And so they tried to work with upstream GDB and get the patches pushed upstream, but were completely unsuccessful. Basically, it was expectations on the GDB side that either they couldn't meet or couldn't keep up with the pace of ongoing upstream changes. I'm not sure of the exact details, but this is a common theme I've heard, that it's often very difficult to work with the GDB and GCC upstreams, at least from the FreeBSD community. And of course, GCC is the same sort of thing. We've imported lots and lots of versions. It's a bit more frequent, and a few sort of more odd things where we've either waited a long time, or some of them actually even go backwards because we imported a snapshot and then updated to the eventual final release. And if we extend the history out to today, I've skipped quite a few releases. I put GDB 7.0 to show a new major release came out just before 2010, and GDB 7.8 is the most recent. I think it was just this last July. So of course GDB development is still ongoing, and we've stopped as of 6.1.1 in 2004. So in the base system in FreeBSD today, we have a 10-year-old version of GDB. And it's really showing its age. So C++ debugging is really lacking in our base GDB. and threaded inferior target support is also not particularly good right now. And basically what ended up happening at this point was the developers who were doing this work kept, I guess got tired of the effort of always trying to bring in the new versions, and basically just gave up, given lacking sufficiently important bug fix or new feature in those next few releases. There was no real desire to put in the effort to do the import. And then you'll notice that GCC also stopped, and that's when the GNU project switched to GPL v3. And so GPL v3 has a number of new restrictions and new clauses that some major FreeBSD committers and FreeBSD consumers and contributors to FreeBSD, sort of outside of the committer base, found onerous or objectionable. And so the FreeBSD project, the current stance is that we won't take a update from a GPL v2 component in the base system to GPL v3 without very careful consideration by the core team to determine if that's the way we want to go or if there's something else we'd want to do. So with the compiler side, we've switched to Clang and LLVM. 10.0 has Clang as the system compiler for the main tier 1 architectures, and that's working out quite well for us. In the base system, as far as the compiler goes, I'm very happy with it. It compiles almost a very large portion of the ports tree and works quite well. So that's been a very successful transition. And then over time, the additional other architectures like MIPS will transition to Clang as the system compiler as well. So it was clear that we needed a new debugger. We had no path forward, and we had no way to move forward, and the GDB that we had was increasingly showing its age and becoming a problem. So at the time, there were a few debugger projects out there, open source or otherwise, and a few new projects started springing up within the FreeBSD community and in the broader open source community. But none of them really gained critical mass and became a viable option for the FreeBSD base system. And then in 2010 at Apple's Worldwide Developer Conference, WWDC, they announced that they had been working on a debugger project called LLDB, and it's built on top of Clang and LLVM as foundational libraries. And it basically it follows the same model as Clang and LLVM as far as it's in the same family. It's now in the same repository and uses the same bug tracker. It's a member of the Clang and LLVM family. So just looking briefly at LLDB's history, this is the chart just represents lines of code data from Black Duck Open Hub, which used to be called OLO. And from mid-2010 to about mid-2012, it was really an Apple project. I looked through the commit history in the repository at email address, domain names, and basically speaking, Apple did pretty much all of the work during this time. I did look to see who the most prolific non-apple.com committer was, so I looked, and it turns out they were responsible for just under 2% of the number of commits during this time period. And so I wanted to see a little bit more about what they were working on and what the relationship was. And it turns out they were actually an intern at Apple during this time, and their email address switched to apple.com later on in the history. So I looked at the next most prolific committer, and they were responsible for about 1.5% of the commits, but notably including some initial Linux support. So during this time, a few patches landed for Linux support and for a very initial port to FreeBSD. So FreeBSD developers, Mark Peek and Kip Macy, did a lot of the early work, and there was someone else even before that that went in during this time. So the Linux support existed in LLDB, and then Kip Macy and Mark Peek took that, refactored that support into a set of POSIX classes, and then had FreeBSD classes and Linux classes that derived from the POSIX base class. And then starting in mid-2012, Intel's open source group in Waterloo, Ontario, Canada, just down the street from where I live, started working on this. They had about, I think they had 4 committers fairly consistently developing LLDB, and their primary focus was on Linux, so they wanted it to be a very capable debugger on Linux. And there were a few other people at Intel that were committing at the same time, but primarily a small group was doing quite a lot of work. And then in early 2013, I started working, and that little bump there is it's just an anomaly of the data from Black Duck. It's not that I was a very prolific committer just doing all kinds of work. What really happened there is one of the Intel guys committed a whole bunch of API documentation, and OpenHub counted that as lines of code. So it looks like I showed up and did a ton of work, but really it's just a little glitch. So my interest in LLDB came from a few different areas, but one of the motivating factors is the work I'm doing with the computer lab at the University of Cambridge, as mentioned, in collaboration with SRI in the US on a DARPA-sponsored project for hardware compartmentalization at the instruction set level. So this introduces a whole bunch of interesting new requirements as far as registers and memory attributes and things that need to be just shown in a debugger context. So that's one of the reasons that I started getting involved in LLDB. But in order to be able to explore some of those new avenues, I first had to go and do a lot of work just to get LLDB on FreeBSD into a good state. So when I started, the port had bit rotten a little bit. It didn't even build, actually, on FreeBSD. And so I had to first fix the build issues, and then you would start it, and it just basically didn't actually work. So solving a few of those issues, finally I got to the point of it's usable as a basic debugger. You can start up bin ls, set a breakpoint at main, and it actually does something. And then I worked on the test suite, so it was the same sort of thing. At first, the test suite didn't run on FreeBSD, and I had to do a whole bunch of things to get it to pick the right compiler and the right libc++ and those sorts of things. And it's not a lot of difficult work. It's just tedious to iterate through all of those special cases where they've got, if platform starts with Linux and et cetera, and then just adding a FreeBSD case on the end. But there were a lot of those sorts of little things that needed to get cleaned up. And in the beginning of this year, Google has come on board to start doing a lot of LLDB work as well, which is really important because the Intel guys, that group has actually shut down now. The office down the street from me has closed, and they're not working on this anymore. And there's a lot of work to do here in sort of the base infrastructure beyond just porting to Linux or porting to FreeBSD as well. So it's excellent that another company with significant resources has taken a large interest in LLDB. And their primary platforms of interest are Linux, Android, and they're doing some work on Windows as well. And then I looked through the rest of the commit history to see who else has been involved, and I just put some of the logos based on domain names that I found in there. And there are quite a few people who are doing 1 or 2 patches here and there, build fixes and things. So my point here is really just that LLDB is very much transitioning from what was originally an Apple project to what is now very much a community-supported and very credible and viable debugger. So I'm going to talk a little bit about LLDB's design. And so LLDB, in a similar way to Clang and LLVM, is built as a modular set of components that can be reused for other purposes. So LLDB actually it's built as a library that other projects can link against and use its functionality. So it's designed to vend an API, and if you're writing a command line debugger, so you type LLDB at the command line and you're using it through a UI or through a text interface, it's actually just linking against liblldb the same way that if you're using Xcode on OS 10, it's linking against the same kind of LLDB library underneath. And you'll see Python actually on here in 2 different spots. So Python's on the top as a consumer of the LLDB API, and then it's down here as a script interpreter. So For the top case, you can write a Python script that says import LLDB, and you basically get an LLDB object that you can then have start up a process to debug, set breakpoints, single step through it. So you could write an entire debugger front end in Python, for instance, just using the library under the hood without actually having to run a LLDB binary that, that you communicate with through some sort of interface. And then the Python down here in the scripting interpreter is something that we don't have at all in the base system today. In GDB, the scripting interface there is quite limited in what old versions of GDB can do. Newer GDB, contemporary GDB, has a Python scripting interface as well, but it allows you to do things like if you need to walk a linked list that's in your target process, for instance, you can write a script in Python that will read member variables and do whatever you want to do so that you can automate the sorts of tasks that you need to execute like that. You can also use the script interpreter built into LLDB to add new commands, new functionality. So for instance, there's a memory search command that someone added at some point, and that's actually implemented in Python. The expression parser up here is one really interesting part of the way LLDB works. So as you can see, I mentioned that the orange parts there are components that build heavily on Clang or LLVM, build on top of Clang or LLVM foundation parts. So the disassembler in the plugin side is one part. LLVM provides the disassembly capability. But the expression parser is really neat. So one of the challenges of a debugger is giving a faithful expression parser. So you can type in something at the command line to examine some complex object and examine member variables in some really complex variable you have in the function that you're stopped in the debugger. And what LLDB does is takes the expression that you've entered at the command line, wraps it in a function sort of wrapper and a template, and not a C++ template, just a boilerplate around your expression, and then passes it off to Clang to parse it, so that any expression, any code that you could enter in your original source that you've compiled and are now debugging can also be entered at the command line and have LLDB through Clang execute that. And so what LLDB does is takes the Clang AST, does a few transformations at that level, converts it to LLVMIR, does a few more transformations at that level, and then depending on what sorts of operations your expression actually performs, it either has an IR interpreter that can figure out if you're just reading a simple variable, it'll just do that without doing anything particularly complex. And if you have if you have a more complicated expression that it can't interpret, it will JIT it and execute it in your targets, in the context of your target, so that you can do sort of any function call you want. There's certain limitations, but generally speaking, you can execute any sort of function call you want. You can define local variables in your expression context that will remain from one expression to the next. And I'll show a very brief demo of that later on. The data formatters are one other item I'll talk about just briefly. So this is built into LLDB, and it knows how to interpret the libstandard C++ or libc++, any of the sort of standard classes, so that you get a nicer looking representation for standard string or map or vector or whatever, rather than just splatting out a whole bunch of incomprehensible gobbledygook. And that's something that contemporary GDB does through bringing in a Python script as well, but in the base system today, we don't have that capability. And I don't really want to talk about GDB versus LLDB too much because it's not really a valid comparison to say contemporary LLDB does so much that 10-year-old GDB doesn't do. It's not really a very useful discussion. But I think one of the things that's very interesting is even compared to contemporary GDB, the discussion is very much around what can one do that the other can't. And I think we'll see over the next couple of years, as we've seen with Clang and LLVM, the early discussion was, how does this compare to Clang and LLVM? How does it compare to GCC? And we've largely moved past that now. We're largely talking about what are the interesting things we can do because of the way that Clang and LLVM work, and what can we build on top of that. And I think in the next couple of years, we'll see the same thing with LLDB, where we won't be comparing features or saying what isn't implemented yet. It really will be, what are the cool things that we can do with LLDB because of the way it's built. And this is just a close-up of the plugins. I'm not going to go through all of it, but I've highlighted in blue the ones here that either had to be written for FreeBSD or that FreeBSD heavily relies on. And the process plugin there is probably the most important one. It provides register definitions and the concept, any sort of thing that is specific to a FreeBSD debuggy, the FreeBSD target. The platform represents running LLDB on a FreeBSD host, so things like copying files to or from the host system. I'll describe briefly how LLDB looks from actual use. So GDB's command parser has evolved over time to have all kinds of overloaded, all the commands can take all kinds of different options depending on what context they're in without really knowing exactly what it is. So for example, the breakpoint is the best example. You can set a breakpoint and without really telling it what it is, it can be a function name, it can be a file and line number, it can be a C++ method, and it just sort of hopefully figures out what it is you mean. And LLDB, it's normal, the command parser was sort of designed from the beginning to try and be very regular and discoverable, and so all of the commands are of the form noun, verb, and then options and an argument. So instead of a whole bunch of overloaded breakpoint commands, it would be breakpoint set -- name main. And this is a little bit verbose, but like GDB, you can use the shortest unique prefix of the entire command name. But also, LLDB introduces a whole bunch of aliases so that, generally speaking, the basic functionality of GDB for single stepping or for starting a process or for setting a breakpoint, there is an alias that allows LLDB to work with your finger memory from GDB. And most of these are just direct aliases. The command works exactly the same way or doesn't take any arguments, but the breakpoint command is actually a specific, the B command, sorry, in LLDB as an alias is a specific command that's implemented to try and handle some of the overloaded options that you can provide to GDB's breakpoint command, but it really, it's a much limited set. So if you're going to use LLDB, it really is a good idea to sort of try using to get familiar with LLDB's native commands. And so I'm going to give a very brief demo here. So I have here the text of Romeo and Juliet from the Gutenberg project. And this is actually an example from LLDB's website. So if you'd like to try it out, you can follow along there. And so the application here is just a simple dictionary that will read in that entire file, accept a word, and then tell you if it's found in the file or not. And it builds a binary search tree from the file that you type in, and then just shows you if things are found. So, for example, if I type in words that I would expect to find, in Romeo and Juliet, they're found. And if I type in words that would not be expected, not found. But if I type in a word that should be in there, it says, oh, it's not in there. And so that's the bug they've introduced in this hypothetical example. So let me just... So you may have to bear with me if something doesn't work here, because this is actually a development snapshot as I've been working through a number of issues on my my working directory. But so we'll start up LLDB with our buggy example, and first we'll set a breakpoint. There's a find word function that takes the word that the user has provided and performs the binary search. So as you'd expect with the debugger, it stopped at our breakpoint. It's given us a little code snippet, and it tells us that we stopped. The reason is a breakpoint, what thread ID we've stopped in, the instruction pointer, our application, and the function that we've stopped in, and the function's arguments. And we can get a backtrace, etc. So one of the really interesting things we can do with the Python scripting is write Python to be able to understand the same data structures that we use in our C code. So if we say type in script, we get a Python interpreter, and I will just cut and paste this so I don't have to type it all. So tree utils is the little snippet that's provided that can understand the binary search tree that's in our code. LLDB.frame.find variable is just looking up a variable in the frame that we're stopped in, and we're asking it to find the path to the word that we expect to find there. And so the Python has told us that we should go right, left down the tree and find the word that we want to see. So if we look here, this is the find word function that we stopped in, and we can see line 134 and line 136 are the two branches for taking the left or right branch of the tree as we search. And so I will add a Python script. So I'll set breakpoints at the two return statements as we're going to go through the walk the tree. And now we can add a snippet of Python to run when we hit the breakpoint, and it gives a quick little help discussion here, or a description about variables that you'll have to use in the Python that you're going to enter. Just oops. And so what we're asking for in this little Python snippet is we have that path variable that we calculated using the Python version of the tree walking earlier, and we're saying if the first character of the remaining path is R, and we're in the right return branch, then we'll just strip that one off and continue. But if we actually take the left branch in the C code and we know we're supposed to go right to be able to get to the word that we're looking for, we'll print out a little statement and not continue. So there's all of our breakpoints that we've set. So we'll disable the initial find word breakpoint, and we'll restart. Oh, and this is, there we go. There's a little bit of a race condition with I/O handling in my current debug snapshot. So in this specific case, sometimes you'll see the LLDB prompt came back out here. LLDB's command interpreter popped up on top of the target I'm trying to run. So I just tried again. And now I've rendered Romeo again, and we've stopped and printed out the text that we had in Python. It says, we're going down the right branch, and we should be going down the left. And if we look over. So we can just type script and then a one-line Python if we don't want to actually enter the Python command interpreter and then quit afterwards. And it's telling us that this is what's remaining. So we had RL, RRL, and we stripped off the R, and then this is the path that we should still be taking, but we've taken the right path. And if we say, we can look look down the tree with the path that we've expected, and there's the word that we want to find, and if we say the word we're looking for, that's the word we're looking for. And I mean, this is a bit of a contrived example, so, oh, there's the problem. It's we've uppercased or lowercased the words as we've inserted them into the tree. It wouldn't actually be that easy, of course, but it does demonstrate the sort of power that's available through this sort of interface. Now I'll just talk very briefly about the current status of LLDB on FreeBSD. So the test suite, after a lot of work, runs consistently on FreeBSD. There are build bots that are running regularly on each commit in the upstream Clang, LLVM, LLDB repositories. And the full test suite basically runs. The tests that don't apply to FreeBSD don't. But 311 tests run, and all of the failures have a PR in LLVM's Bugzilla. So initially, there were large classes of functionality that just didn't work. We've moved past those sorts of things, and what remains are some one or two off cases that are maybe not fully understood, but there's the beginning of some debugging information in the upstream repository. And actually, that's one thing that I forgot to mention earlier. I mentioned that LLVM or LLDB is under the same permissive BSD-like license as the rest of Clang and LLVM. But the other really big difference is that the upstream LLDB community is very helpful and very welcoming. So I started doing some initial work to get the build fixes ready, and was submitting a lot of patches. And in very short order, they said, we're tired of committing these things for you. We'd like you to just become an LLDB committer so you can push the FreeBSD changes in directly. And so it was only a matter of a few months of me submitting patches and getting things moving along that I was an LLDB committer. And the rest of the LLDB upstream is very, very helpful to anyone who comes along with questions and talking about ideas for future direction or general things that people would like to implement across a variety of operating systems. In FreeBSD right now, AMD64 is the only target that really works, and LLDB on FreeBSD is a perfectly capable, very usable debugger for AMD64. I said I wasn't going to say this too much, but at least as good as GDB in the base system. i386, there's code in the tree. It doesn't actually work. It's in that same state of, you can't even start a simple process and set a breakpoint at main. And there's nothing in here, I think, that's particularly difficult. It's just some usual 32 versus 64-bit kinds of issues, so some offsets are incorrect or something along those lines. It's just that the i386 support has been a fairly low priority for me, so I haven't spent any time on it yet, while there are more important things to fix in AMD64. MIPS is not usable as a local debugger at the moment, so you can't actually run LLDB MIPS on your little MIPS device, but it does actually support core files from MIPS binaries. And ARM, because Apple obviously cares an awful lot about ARM, LLDB's internals have a lot of ARM support, but it hasn't been brought over for FreeBSD or Linux yet. 64-bit ARM support is starting to come for Linux, and we'll bring that over to FreeBSD as well. It's early days yet, but I don't think it won't be particularly long before LLDB is actually a workable ARM64 debugger on FreeBSD. SPARC64 has some volunteer effort, PowerPC has some volunteer effort, and then SPARC64 and IA64, I don't know if anyone is going to actually work on getting those working. So I've looked through this over time, and it used to be that a lot of these things didn't work. Basically now for userland debugging, LLDB is great on, and again, this is AMD64. The Watchpoints are one interesting case. Most of this work is work that I've done to get these things to function. Watchpoints was actually contributed by another developer at a company called Zinuous. So it's even within the specific domain of LLDB on FreeBSD, I'm not the only one doing the work. I had a Google Summer of Code student over this past summer working on kernelside debugging. He delivered a workable proof of concept demonstrating that, yes, we can, against a live, running on your live system against dev-mem, or with kernel core dumps. It will be possible, and the project didn't really get as far as I would have liked in order to have something committable to the tree directly, but I'll definitely take that work and refine it to have kernel core and live debugging. And then on the bottom, this is something that will come a little bit later. So for OS 10, kernel debugging is done using UDP over Ethernet, because most systems you want to debug these days don't have serial ports anymore, which is the sort of traditional interface you would have used, or FireWire. That's all disappearing. So at least LLDB has internal support for Ethernet remote debugging, and it has a OS 10 backend for that only at the moment, but by the time we have the stub support in FreeBSD, I'll work on getting the LLDB side in. GDB protocol remote debugging, it's in, and it basically works. It does need some more testing to find if there's any other corner cases that don't work. But what's really interesting is that hasn't historically been particularly useful for FreeBSD, because GDB server hasn't been workable for us. There is a project now called LLDB-GDB server, which is a bit of a strange name. I just call it LLGS. And it is implementing the same sort of functionality. So it's a debugging stub that you run on your target, and the debugger connects to it over some interface and controls your userland process over that interface. It It's being developed by the Google guys for Linux initially, and I have done a little bit of work getting it to FreeBSD, and again, I think it is not yet fully working for Linux, but it's very close, and in very short order, I'll be able to get that running on FreeBSD. So this is very important for embedded targets where you don't have an awful lot of memory and don't have a lot of CPU power. So it uses a lot of the same low-level infrastructure from LLDB, but doesn't bring along the Clang expression parser and all of the higher level, more heavyweight functionality. One of the really neat things about LLDB is that it is inherently a cross-architecture and cross-OS debugger. So in the same way that Clang and LLVM have support for a whole bunch of target architectures built in when you chosen at compile time, you can, but generally speaking, the entire set that's supported, LLDB works the same way. So what it means is I can run LLDB on my FreeBSD laptop, and with that same LLDB binary, I could debug a local process on my laptop. I could connect to a Linux target and do remote debugging of a Linux target, or I could connect to, say, a FreeBSD MIPS device on my x86 laptop using the same LLDB binary. And for the most part, that sort of works. It's because it's not a particularly commonly used case yet. There are quite a few small issues that one will run into when trying it. So really what needs to happen there is just getting a lot more testing and bug reports. And as we find things that don't work, they'll get fixed quickly. LLDB, there's a snapshot in the base system right now. Upstream, FreeBSD development on LLDB, the bleeding edge is upstream. So all of my work is actually going there first now, and then coming into FreeBSD after settling for a little while. But we have a snapshot in the base system. It's not built by default, but if you add with LLDB equals yes to source.conf and the standard build world and build kernel well, build world and install world as defined in the handbook, it will give you an LLDB in your install. Clang 3.5 imports coming into FreeBSD sometime in the fairly near future, and when that happens, I plan to bring in a new update from LLDB upstream and enable it by default. And the last point is that Python is a little bit of a trick because we're not going to have Python in the base system. So some of the more interesting functionality wouldn't be available unless we can do something about this. And what my hope is that right now Python in LLDB is a compile time option. It's very easy to build LLDB with or without Python, but it is compile time. So my hope is to move that to a runtime check, and the LLDB in the base system will magically be able to use Python functionality if you've installed the port. Thank you.
Any question?
The main usage of GDB, special imports, the current GDB, is the machine interface that a lot of the desktop development environment use. LLDB has the same machine interface, is already implemented, it's just Planet, or I don't know, this is the question. If you want to use kdevelop, I could use kdevelop with LLDB, or I have just to use GDB is not yet implemented.
Sorry, can you?
The machine interface.
Yeah.
The GDB machine interface is used to speak.
Right. So GDB implements a machine interface which is a way for front ends to communicate with the GDB binary running. LLDB has actually had a compatible implementation of that contributed fairly recently. So LLDB also can speak the same GDB MI protocol. So that various front ends that know how to speak GDB MI could talk to LLDB MI as the back end. In this case, actually, this is a screenshot from an IDE called CodeLight, which builds on FreeBSD. It doesn't include the LLDB support yet, but the integration that the CodeLight guys have done uses the LLDB native API. So liblldb just links into CodeLight for their use. But yes, any of the other kinds of GDB front ends that speak the MI protocol could use LLDB as well.
Thank you.
Hi, since you mentioned that there were watch points there, are those hardware watch points or?
Yeah, hardware watch points.
Perfect, thank you.
Hello. Just a question. As you had to implement all the FreeBSD specific part, how much work is it? I'm from Minix, so we were kind of thinking of importing it.
That's a very difficult question to answer. A lot more than I expected.
Okay.
For a few reasons. So as I said, when I started, a lot of things were in fairly poor shape. And there was actually a bunch of internal LLDB functionality that I had to fix up for our specific use case that was even independent of FreeBSD or Linux. It was just core internal bits that didn't work properly. So it's a little bit hard to say. Like I said, I've been working on LLDB off and on since the beginning of 2013. I think, though, that with the way things are progressing in LLDB now, it actually isn't going to be all that difficult for additional projects to do a port, because there's been a whole bunch of refactoring that has been going on and is still going on to clean up a lot of interfaces, so it becomes much, much more clear where you need to plug in OS-specific functionality. And also, I think the effort to bring on the next BSD port is much less than what I went through with this part. So NetBSD, there is some initial build infrastructure in there, and basically to be able to run LLDB on a NetBSD host, but not the actual ptrace interface. But I don't think it's a huge project anymore.
Okay, thank you.
Well, hi. Is it possible that you connect LLDB with the open on-chip debugger? Well, obviously, it supports plenty of JTAGs, and it will be quite useful.
So, I mean, I think that OpenOCD just exports the GDB remote protocol, doesn't it? So LLDB can speak that protocol. So that should all just work. There may be reasons that it might be interesting to actually use other interfaces to OpenOCD, but I think in general, it would work the same way GDB does of speaking the GDB remote debugging protocol.
Okay, thank you, Ed.